Hi, everybody, and welcome to our next video. In this lecture, we're going to focus on Chapter 5 and continuous curves, particularly the normal distribution. So in Chapter 4, we distinguish between discrete and continuous random variables, and we learned that continuous random variables have an infinite number of possible values that can be represented by an interval on a number line. Its probability distribution is called the continuous probability distribution. So in this chapter, we'll learn about the most important example here, which is the normal distribution. And the normal distribution is used to model many sets of measurements in nature, industry, and business. So as one example, systolic blood pressure of humans is one example that uses the continuous bell shape or normal curve, the lifetime of smartphones, as well as housing costs all tend to be normally distributed random variables. So there's actually quite a lot of examples of data that is naturally normally distributed. And again, if you see anything that says normal, they're basically talking about all of your data that is bell-shaped. So it looks kind of like this. Other examples tend to be things like IQ scores, heights, weights, etc. So a lot of testing examples too. And like we said, some basic health examples exist as well. So here is your normal distribution. Again, it's continuous. The graph of it is called the normal curve, and it has the following properties. So the mean, median, and mode are all equal, and they occur at the center. Now, if I'm being realistic, we don't really use the median or mode too often here. We tend to refer to the mean as the most important one. So that's why you're noticing at that center here, this lower value there is your mean. If I can switch that up, there we go. The normal curve is bell-shaped, like I mentioned. It's also symmetric, which is really important. So meaning like the left side and the right side are identical. They're mirror images. The total area under the curve, so all of this area here that's shaded in, is equal to 1. Just like with a probability distribution from Chapter 4, in that case, we had the tables, and we were able to check by adding all the values to make sure we had 1. Here, because our values are continuous and there are infinitely many, we can't actually list them in a table. So we use a graph to help us here, but still the same idea is that the total of those probabilities is going to be 1. And what we see graphically is that area under the curve and probability end up being the same thing. The curve also approaches but never touches the x-axis. So it's a little hard to see here, but that curve is hovering above the x-axis and it will continue extending farther and farther away. And then between the mean plus or minus 1 standard deviation, the graph curves downward and then it switches to an upward curve. So here and here, these are called inflection points. And it's basically where the curve changes from more of a downward shape. So like here, it looks like an upside down U, to more of an upward shape, so more of a regular shape U. So in algebra, we say that it goes from concave down, and then this would be concave up. So those are called inflection points. Your inflection points always occur at the mean minus 1 standard deviation and the mean plus 1 standard deviation. So these are again, fixed values that you should kind of watch out for on these bell-shaped curves. Now, an interesting little side note on the left here, you actually have the equation for that bell curve, and you can see it's a pretty tricky equation there. It's not that easy to use. So if you were taking this course as a math major, like in a calculus-based statistic course, then you would actually be using the curve to actually find areas and things like that. But for us, we're going to focus on technology or tables to help us get these values. But there is an equation for that curve, and that is it right here. The first example I want to look at together is just distinguishing bell curves or normal curves. So it says in exercises 11 to 16, determine whether the graph could represent a variable with a normal distribution. So again, normal distribution is that bell shape. Explain your reasoning, and then if the graph does appear to have a normal distribution, estimate the mean and standard deviation. So let's do the first part. Which of these graphs could be bell-shaped or normal. And this is a good time to pause the video and try it on your own first. So a couple that we can eliminate right away, like number 14, this is definitely not bell-shaped, right? It has two peaks there, so that is not a bell-shaped curve. Number 16 as well, this is definitely very skewed. We talked about skewed graphs already where, they're not really centered. This definitely does not look symmetric in any way. So 16 is out. 11 also has a bit of a skew there too. It's not as bad as 16, but it still is skewed. And if I think about that peak, it is not in the center of the graph, right? It's off to the right. So that is not bell-shaped. Now the last three all look bell-shaped. Number 13, there was a problem. When we have a bell-shaped curve, we talked about how it always hovers above the x-axis, whereas this one goes below the x-axis. That is not a correct bell-shaped curve or a normal curve. So we have to get rid of this one as well. Again, because it dips below the x-axis, that should not be happening in a normal distribution. So the only two that actually look like they could be normal distributions would be 12 and 15. So we want to start by estimating this mean and the standard deviation. Now your mean is always going to be in your center. So if I look at this one here and I kind of try to drop a center line down, it looks like the mean there is maybe about 18.5. Looks like it's about halfway between 18 and 19. And then over here, if I drop that center down, again, it looks like it's about 11.5, about halfway in between those two as well. Now, how do we estimate the standard deviation? We can estimate the standard deviation by using the inflection points. So what we can do here is find the inflection points as a start. Inflection. All right, so if I look here, I'm trying to figure out, well, where does it switch from more of a concave down shape to more of a concave up shape? And again, you are estimating here because it is hard to just look and figure out the exact point, but you kind of want to do your best. And I would say that, right around here seems to be where it's switching, and maybe somewhere around here. So if I drop this down here and here, it looks like maybe my inflection points are at about 16.5 and 25. So how do we use the inflection points to find the actual standard deviation though? Well, the idea is that the inflection points always occur at either the mean plus one standard deviation and the mean minus one standard deviation. So this is where your inflection points occur. So if I think about what's going on here, my mean is 18. And if I add something to it, I should get up at 20.5, right? So we're saying, okay, if I have the mean and I add the standard deviation, then I should be at one of my inflection points. So we can use this idea to estimate. And if you think about the change between the two here, this is 18.5, then our sigma has to be about 2, right? If I count from the 18.5 over to the 20.5, that looks like a distance of 2. So I would estimate my sigma is 2 there. And it should work the other way as well. So if I have the 18.5 and I subtract the sigma, I get down to 16.5. And again, well, what's happening there? Sigma looks to be about 2. And we can see it here from the center out to that inflection point, it's about 2 units. So that would be our estimation for sigma in this case. For this one down here, I'm going to do the same thing again. So I'm kind of looking here. Here it's definitely down. Here it's more up. So it's a matter of where are those points occurring. And again, it is not perfect, but you can kind of do your best to eyeball where you think they occur and drop it down. So they look like they occur maybe at 10 and at 13. So you're looking at the change from the center, right? How far is this away? How far is this away? That's really all you need here. So from 11.5 to 13, it looks like a change of about 1.5. And from 10 to 11.5, again, we also see that same 1.5 change. So our estimation for sigma would be about 1 point. Now we also have a specific normal distribution that we use a lot. So it has a special name. It's called the standard normal distribution. And in the standard normal distribution, what happens is the mean is 0 and the standard deviation is 1. And this is always true every time you see that word, standard normal distribution. So at some point, they'll stop giving this to you. You're going to have to memorize that and know that anytime you see the word standard with the normal distribution, that would be the mean and the standard deviation. So you have your bell curve. Again, your center is right at that 0. And what happens is the horizontal scale, so the horizontal axis, ends up being z-scores instead of the original raw data. Now, there are some data points that we do see in z-scores often, but most of the data we see tends to be, X value data, so just that raw data that we collect. But we can shift everything to make it into a z-score if we want to put it in the standard normal curve. And we can do that by using this formula here, where we take the X value and subtract it with the mean, and we divide by the standard deviation. So for instance, let's say you have a data problem and you collect some data and you do some calculations and you find that the mean was 10 and the standard deviation was 2 and one of the X values is 4. Well, we can make this into a z-score by using this formula. So I take the X value and subtract the mean and divide it by the standard deviation. So I do 4 first, my mean is 10, and then I would divide that by 2. The order is really important. The X value has to go first, and then we subtract it with the mean, so we get -6 here. And when I divide that by 2, I get negative. We typically use 2 decimal places with z-scores. There are some exceptions, but this would be the same as, -3 or -3.00 here. So every single X value can be translated into a z-score. And again, this can be helpful for different reasons. One of them is because our table in the book is all in z-scores. So that is an application there of why we would want to change all of our X values into z-scores to use the standard normal curve instead. All right, so let's actually look into some more of the math here. So this is a nice graphic of the 3 things that can basically happen, or 3 of the main things that can happen when we're looking for the area. So here we have 3 things. We're going to use the standard normal curve in each case. So our centers are all at 0. And again, your axis here is a z-score, not an X value. So we're just talking about our z-scores here, our standard normal. When we're talking about area and probabilities, I highly recommend you draw a picture every single time. I think it's really helpful to see that visual. So in the first example, we're going to find the area to the left of z. So in this first case, our z-score is 1.23. So you can see we're starting with the 0 in the center, and then you're graphing that z-score right here. And then because I want the area to the left, we're shading the whole area to the left here. Now, because this is symmetric and the area underneath is 1, I always like to estimate what I think it's going to be, right? The area under the entire curve has to be 1. So I'm shading definitely over half of this, right? If the center is halfway, I'm going to estimate that maybe this is like a 0.8 or something like that, right? So I'm definitely over the halfway. I have most of this shaded in. Now, how can you find these values? So you can use Excel. So if you want to use Excel, I have videos I suggest you watch. And you can do them on Excel. Or if you want, you can use a table. So the table that we're using is table 4 from your text. And there's positive z-scores on one side and negative z-scores on the other. And so here, let me show you how to use it. So we're looking for z is 1.23. Now, on the left of your table, you have the first 2 digits. So here I have positive 1.2, which is right here. And then my next digit is 3. So if I scooch over here, I can see the 3 is right here. And I'm going to match up that column and row, and that is going to give me that final answer. Now, the other thing I want to point out is that this table, if you look at the shading here, is always area to the left. So that's important to note that your table is always area to the left. So if you're looking for area to the left, you're just going to pick up the value that's in the table. So this is how they get the answer of 0.8907. So again, anything that is about area to the left, this is also called cumulative area. You're either just going to read the table or the Excel value as it is. Okay, and again, you can see the other video if you need that reminder of how to do it in Excel. Now, the next example, they're looking at the area to the right, and we're going to use the same z-score here, but they're looking at this area on this side instead. Now, notice that this area is much smaller, right? So it's definitely less than a half. So I'm expecting something pretty small, maybe like a 0.1 or 0.2, something like that. So how do we find the area to the right? So if you have a question about the area to the right, what you're going to do is 1 minus whatever the area to the left is. So your table only does areas to the left. It doesn't go both directions. However, the total area under the curve is 1. And these are opposites, right? Left and right side would be opposites. So if I know the area on the left, I can subtract it with 1 to get the area on the right. And that's what we would do here. So we already found this z value already. So I would do 1 minus that 0.8907 we got. And that's how they're getting 0.1093. And again, it'd be the same thing in Excel. So in Excel, when you look at those videos there, it will spit out always the area to the left as well. So you're still going to have to subtract with 1, even if you're using our Excel formula. And as a side note, so you need that little reminder, the Excel formula is the one that says normal dist. So it's normal distribution there. The last one is how do you find the area in between two z-scores? So if you're going in between two z-scores, what you're going to do is find both z-scores in the table first, or in Excel. That's what you're using. And then you're going to subtract them. So we already found the z-score, the area for the z-score of 1.23. We saw that was 0.8907. And the other z value we're doing here is negative 1.75. Negative 0.75, excuse me. So my first two digits are negative 0.7. So I go to my negative side of the table. I'm going to find negative 0.7. And then my next digit is the 5. So I'm going to go up here to the 5 column. And I'm going to just kind of look down until I can match that answer up with the row. And that is going to be that area to the left. So this one is 0.2266. Now, because we want the area in between, we're basically going to subtract these because we're taking the whole area to the left and cutting out that extra tail piece on the end that we don't need. So we're going to take that 0.8907 and we're going to subtract it with 0.2266. And that is how we get 0.6641. And again, make sure your answer makes sense. I do have quite a bit of shading here, so I think 0.66 is very reasonable in this case to get that value. As a little side note, just for some different notation, another way to write this would be that the probability of z is less than or equal to 1.23, or z is less than 1.23. Those are both considered correct. Where it's continuous, you get the same answer in both cases. It's not true for discrete data. For to the right, another way to write this is the probability that z is greater than or equal to 1.23, or again, just greater than. So that notation also means the same thing here. And if you're going in between, we can write that as negative 0.75 is less than or equal to z is less than or equal to 1.23. Or strict less than signs. Again, for continuous data, it doesn't matter like it does for other examples. Now, I encourage you again to pause the video here and try out the next page on your own, either using the table or using Excel, to see if you can get these for values. And when you're ready, you can come back to the video and see how you did. All right, so if you're not pausing, I'm going to keep going, but otherwise I really do encourage you to try these on your own first, just so you can see how you do. I'm going to use the table in this case, but also I encourage you to try Excel if that's what you're more comfortable with. So I am going to draw the picture in each case, and I do want you to notice that all of these are z-scores. So because they're z-scores, our center is always going to be the 0 there. All right, so my center is at 0. I'm going to the left, and my z-value is positive 0.17. So I don't know the exact, position, but it just has to be, somewhat accurate. So it's definitely going to be in the positive, so it's to the right of 0, but not too far over. And I want the area to the left, so I'm shading in this piece over here. Now I'm going to estimate that it's going to be over a half, right? Because I'm definitely have over half the graph shaded, but it's not that much over a half, so maybe like 0.55 or 0.6. That's my guess. And now I'm going to go ahead and use the table. So I'm on the positive side. It's 0.1. So right here. And then I need the 7. So the value that works there is going to be 0.5675. Now, because it's area to the left, you are done. That's all you need to do. In the next example, we're going to go between two values. So I'm at 0 for my center. Now, one of my z-values is actually going to be 0 this time. And then I have another one that's positive. And I'm going in between the two. So my area is definitely less than a half, right? But it's going to be probably pretty close to a half. Maybe like 0.45 is going to be my estimate here. Because I do have a lot of it shaded in. So when you're going in between, I need to find both of the z-values in the table. So for z0, as a little side note here, you can see it right here. And it's going to be exactly a half. So your area here is 0.5000. And then for 286, I'm going to come down here to 28. I'm going to go over to the 6. And I have something pretty high, 0.9979. And then when you're going in between, you're going to subtract. So we're going to take that 0.9979, subtract it with 0.5000, and we get about 0.4979 as my final answer there. Which makes sense, right? Because you have a lot shaded in. There's very little data after z equals 3, so this makes sense that it's almost a half. And you'll see that your table actually kind of times out at 3.4. Typically after that, you're probably going to just estimate it as 0.9999. So on both sides, your table does stop at a certain point. You can see, again, it gets very, very small here. And anything beyond that, you can probably just estimate as 0.0001. Because the data gets very, very small after you get past z equals positive and negative. All right, next example is to the right. All right, so center is 0. My z is positive 3.25, and I'm going to the right. Now, this should be really small because I don't have much data after the 3s. So I'm estimating something very small. And I have 3.2, which is right here. And then I need the 5. So if I look at my chart, I'm going down this column right over here, and I'm getting 0.9994. Now, because it's to the right, don't forget we're going to subtract. We're going to do 1 minus that value. So 0.9994. Now, my calculator says 6e to the negative 4. So when you see something like that, if yours is doing this, yours may not, that basically needs to move the decimal to the left 4 spots. So you're going to take that 6 decimal point is on the right, and you're going to go 1, 2, 3, 4, and then you can fill in any holes with zeros. So the answer here is going to be about 0.0006. You could also just subtract it, using regular subtraction. And do it that way too, if you find that easier. All right, my last example here, and this one is a little bit different, so I kind of like this one. Again, still z-scores. So we're going to the left of z equals negative 1.28, so this area. And then we're also going to the right of positive 1.28, so this area. And because it's an and idea, we're going to end up adding these together. So I know and in probability is usually multiplication, but here the word and just means that we're taking the left tail with the right tail as well. So we're trying to put those two pieces together. So we're going to add the outcome for those two pieces. Now let's do the left side first. So I have negative 1.28. So negative 1.2 is right here. And then my 8 column, so 0.1003. And then for the part on the right here, I have to find this value first. So 1.2. And then I have the 8, which is way over here. So 0.8997. Now, don't forget though, because this one is to the right, we're going to do 1 minus 0.8997, right? So when I do that piece here, and I do the subtraction, I get 0.100. Now, if you're wondering and saying, well, hey, these are the exact same values, that's not a coincidence. And the reason is because our normal curve is symmetric. So you actually can save some work. If you recognize that you actually have the same z values, but one is negative as one is positive, and you're going into the tails, right? So that's a little bit different. Like we're not going in between, we're going into the tails. This tail side has to be the same as this tail side. So if you know this one, the other one will actually be the same. So I can add up those two values here. And I have, let's see, 6002. So 0.2006 for my values there. Again, if you want to try some stuff in Excel, okay, let me come back to my, let me reshare, make sure this is sharing okay. So here is my Excel file from the video. Again, you can just try a couple of these. So for instance, the normal distribution, so we don't need this one yet at the bottom. We can ignore this for now. So the formula for Excel is normal distribution, and then you're either going to type in your X or Z value, your mean, and your standard deviation. So if I just look at the last example we just did, so we were focusing on a Z value of first, negative 1.28. So to use that function, I would start by looking for the normal distribution function. So I like to just type an equal sign, and I start typing, and it says normal distribution. My X or my Z value was negative 1.28. In this particular case, my mean was 0, and my standard deviation was 1 because I had the standard normal curve. And then you do always select true here for this particular function. And when you hit the equal sign, you can see there's the value that we had. Now your table always rounds to 4 decimal places, so that is why it looks a little bit different at first. Here we're going out a few more decimal places. But if you round to 4 decimals, you do get that same 1.003. If you want to do the other side, we were using the positive 1.28. You could change to that instead. There's that 8997 that we saw, and then we were able to subtract it with 1. So you're still doing similar processes and doing this kind of part by hand, but that normal distribution formula will basically replace your table if you would like to do it this way instead. All right, I hope this was helpful for you. If you have questions though, please reach out and I'll see you guys next time.